We are going to conclude this class with section 12.5. We're going to be talking about the normal curve, and this is the homework. Make sure that you do each one of them carefully. This section of the course requires special attention as we're dealing with material that it might be a little bit difficult to grasp, so you need to spend some time figuring out what's really going on in this regard. Let's get started. We're going to be covering the normal curve, and also known as the normal distribution. So when we did the histogram, we drew something like bars to tabulate and sketch all the different points of the data that we have. And from this, we basically plotted, and if you were to smooth these curves, you will get something like, if you were to smooth this curve, you will get something like this, right? And this is skewed to the right. Okay, the numbers are decaying toward the right here, and it's skewed to the left. The small numbers are to the left, and then they go like that, right? So that's more or less what's going on at the bottom here, and the mean basically is moved not at the peak, but somewhere after. And over here is the mean is before. Okay. This will be skewed to the left. So these are skewed distributions. But the theme that we're going to be covering in general is called the normal curve. So in a normal distribution, basically you get something like this, like asymmetrical. This is very important that we, from the very beginning, recognize that the shape is symmetrical. When we smooth this curve in the center here, if you were to fold it, it would be a symmetrical shape. So this is if we just remove the different histogram here, and we just have the smooth curve. This is a normal distribution, and also called the bell shape. And an important thing is that the mean is right at the center. This is a very important curve that we need to know, especially as we continue to do studies or read papers that has to do with statistics. Make sure that you recognize them and to apply the statistical tools to calculate numbers. And now, when you have a normal curve, depending on the spread, this is how a spread the data is, right? It's wider. That means that the curve is spreading or is contracting, right? But it's maintaining the shape where the mean is always at the center. This is a special curve that is used in the statistical calculations. So the normal curve, as I said earlier, is symmetric. And in the normal distribution, all these numbers like the mean, the median, and the mode all have the same value. So this is a very important characteristics of the normal distribution. Now, before we get into the curve itself, it's important to recognize that we need to calculate percentages of the curve. And I had been talking to you about the circle as to how we divide the circle in percentages. It's like you have a pie of pizza, you cut it into pieces, you can calculate percentages depending how you break the circle or the pie. And this is very easy for us to look. It's something that we are very familiar with. However, when we are to the point that we need to calculate percentages on the normal curve, it is going to be somehow difficult, because the shape that we're dealing with has to do with the bell shape. So the question is, how do we divide this one? It's not as simple as the circle. So for that, we're going to be talking about the empirical rule. And the empirical rule is something that you have to memorize and remember it in order to do calculations. And we have to learn how to remove pieces of the bell shape. So the bell shape represents 100%, like the circle represents 100%. And this one, by the way, we always say approximately 100%. And note that for the bell shape, these two lines at the end here, they never meet, right? They don't touch. This guy here, they never touch. They just continue to go like this, and they just barely come close to the horizontal line here. That's why we say that it's an approximation, because it never closes shape. So we're going to be doing something like this, and the first thing that we need to do is learn about the empirical rule. And the empirical rule is used for any normal distribution, or it could be an approximation too. If you have an approximation, we say that we can use this empirical rule. So this is basically a tool that we have. And the empirical rule is for any normal distribution. And this is the rule. 68% of all the data lie within one standard deviation in both directions. The second rule is 95% of all the data lie within two standard deviations in both directions. And the last one is that 99.7% of all the data lie within three standard deviation in both directions. So if we were to look at the shape, I have prepared a drawing here. So basically here what we have is the bell shape, normal curve, right? And we're going to apply the empirical rule. And in this case, what it's telling us is that within one standard deviation from the mean, once to either side, we have 68%. All the data fall in within 68%, whatever is in this portion here will be 68%. When we move to the two standard deviation, there will be 1, 2 standard deviation, 1, 2 standard deviation from the mean. So either from one side to the other, we have 95% of the standard of the data. So in this portion, we have 95% of the data. And when we have the 3 standard deviation on either side, right, this side from the mean to the other side here, we in that case, 97.7% of the data falls within all this chain up to this point. So this is very important to know. We're going to be doing some calculations using this empirical rule. Now I have provided here more detail on the distribution of the percentages. Remember that for the pi, it's easily calculated, right? Because in the pi, basically, we can cut it in half, or we can have it, right? For the pi, it's so simple, right? We cut the pi in half. We know 50% is here, 50% here. We cut it in 4 pieces. We have 25%. But when we got the normal curve, then here, that basically is not that simple. We have to sort of know how every piece of this curve is divided up. So we have within 1 standard deviation from the mean, we have 34%, right? Total is 68. That's the first rule. The second rule is that from -2 standard deviation to +2 standard deviation, we have 95. So we have basically 13.5 plus 34%, plus 34%, plus 13.5%. The whole thing here would be 95% of the data. And then for the 3 standard deviation from -3 to +3, at this point here, we know we have a 99.7. And so we add here 2.335 and 2.235. So what is left on either side is 0.515%. And remember, these lines, they never meet. That's why this is always an approximation. Even though sometimes to simplify things, we call it 100% for convenience. We do that, of course, to simplify the calculations. And so now we are going to do an example. Example 1, you find it on page 769. And it talks about the heights of females that are the same age and that they are normally distributed, right? So this is a key word when you're dealing with this kind of problem. It would be a normally distributed bell shape. Also, it's also known as the bell shape. It says a random sample of 100 females determine the question is determine the approximate number of females in the sample who are expected to have a height, and then they tell you within 1 standard deviation of the mean, and they said B will be within 2 standard deviation of the mean. So basically, we need to use the empirical rule to calculate this problem. And the solution. So the solution is like this. By the empirical rule, about 68% of females have a height within 1 standard deviation. The sample is equal to 500 females. So to calculate this, we know that the number of females will be 68% times 500, and that's equal to 0.68 times 500. So the number will be 340 females. Will be within 1 standard deviation to either side, right, of the mean. B, by the empirical rule, approximately 95% of females have a height within 2 standard deviation. Remember, the sample is 500 females. Therefore, the number of females will be 95% times 500, which is the sample, and that gives you 0.95 times 500, and the answer would be 475 females will be within 2 standard deviation. So make sure that you pay very close attention to the empirical rule. Is something that you need to know in your mind, right? Where we get the 68% is for within 1 standard deviation, and for 2 standard deviation will be 95%. So this is where these percentages are coming from. So that's example 1. Here we have an example that is not in the textbook, okay? But it's a very important example. This type of calculations are done in quality control. So wherever you go in any industry, wherever you go to work, most likely there will be a group of people who will be considering the quality of the materials, products that are produced. So here we have an example where testing indicates that lifetimes of 1,000 light bulbs are about normally distributed, right? When we hear normally distributed, we're talking about the normal curve. Within a mean, that's the mean right here, of 100 hours, and a standard deviation, we have this lowercase sigma here, of 8. So here they're giving us the mean and the standard deviation. How many light bulbs will last more than 116 hours? Okay, so this will require us to do some manipulations on this information that is given to us, the mean and the standard deviation, and to draw the curve. So let's do that now. So normally what we need to do is create a shape like this whenever we're calculating these problems, right? And we go right to the center, and we know that that's the mean right here. And the mean is equal to 100, right? So we can write it for clarification. We can say something like this, right? That the mean is equal to 100. And then we know that the standard deviation is 8, so we start from the mean, we start to add 8, will be 108, will be our first standard deviation. And then we add another 8, that will be 116, and this will turn into our second standard deviation, right? If we would like to calculate the next one, it will be plus 8 over here again, right? But in this example, we only need these 2 points. So now the question again, the question is how many light bulbs will last more than 116 hours? So of course, they're asking us the light bulbs that will be on this side of the curve. This is what they're asking us. What is going to be on this side of the curve? So this is the question right here, basically. What is going to be on this side of the curve? And to do that, we recognize that we can cut the bell shape in half, so we get 50% and 50%, right? Because if we fold this, it's a symmetrical shape, so 50% of the data will be here, 50% of the data will be here. Now, we know to some degree what's here because we have our shapes right here, right? So we know what's here and what's here. Or we know that within 2 standard deviation, if we get the whole shape, right, for the 2 standard deviations right here, we know it's 95%, but we only need half. So we will have 95 divided by 2 will be just this part here. the one that is indicated in the red, right? That would be 95% divided by 2. That's equal to 47.5%. But the whole shape, we can say that it's about 50%. When we say that it's about 50%, what we're saying here is that whatever is left is going to be 50 minus 47.5%. So the end result that is on this piece that we have here left is 2.5%. So this is only a percentage that we calculate on the shape. Now, in terms of the numbers, how many light bulbs, right? That was the question. So the percentage of the light bulbs above 116 hours lifetime is equal to 25%. We got calculated that from the curve. Therefore, the number of light bulbs that last more than 116 hours is going to be equal to 2.5% times 1,000. So now we calculate this one. We put 2.5 divided by 100. We remove 2 here, so it will be 10 times 2.5, and that it will give you 25 light bulbs. Okay, so this is the way we calculate using the empirical rule. Right, we get a percentage of the curve, and then we multiply it to the total sample, and it gives you the number of devices, in this case the light bulbs. How many will be more than 116 hours, so they will last more than 116 hours. This is the way you calculate that. Now, we have been talking about the empirical rule. Remember, the empirical rule has to do with percentages that fall within 1 standard deviation, or 2 standard deviations, or 3 standard deviations. So now the question now comes, what do you do when the data point that you are interested in is in between these points? Okay, so now the situation changes, right? And for us to be able to calculate points that fall within the standard deviations, not exactly on the points themselves, we need to use the concept of the Z-scores. They also called standard scores. And there is a formula to calculate the Z-score for a value on the x-axis right here. Remember, this is the value that you pick, right? Let's say, for example, you pick this value, right? That will be the calculation of the x, right? This is just for us to remember that we calculated this particular point. So the formula said that the Z-score for x is equal to the value of the piece of data, which is in this case this one here, minus the mean, right? So this is the mean, and the sigma is our standard deviation. So we need to know the mean, we need to know the standard deviation, and we know how to calculate those terms manually. We already, early in the chapter, we calculated those. So this is where we come together and try to solve problems that are in between the standard deviation points. We have an example here. It's example 2 in the textbook. And it's stated as follows. A normal distribution has a mean of 60 and a standard deviation of 60, okay? So that's what we have. They're giving us the 2 data points that we are interested in, right? So we can, in essence, sometimes it's good to summarize. On the side, you can write something like is equal to 60. And we need to know the standard deviation. And the standard deviation for our case here is equal to, so standard deviation is equal to 15. So those are the data points that were given, and they want to, the question that we have, this is the question, or questions, determine the Z-score for the following: A 75, B 81, C 60, D 33. And we need to use this formula, and by the way, this is like a shorthand, right? The value that we're interested in minus the mean divided by the standard deviation. Okay, so we move on, and we have the solution here to the problem. For example 2. So the Z-score for 75 is going to be equal to 75 minus the mean divided by the standard deviation. So this results into 15 divided by 15 is equal to 1. The Z-score for 81 will be equal to 81 minus 60 divided by 15. 21 divided by 15 is equal to 1.4. The Z-score of 60 is going to be equal to 60 minus 60 divided by 15. This will be 0 divided by 15. That's equal to 0. And the Z-score of 33 is going to be equal to 33 minus 60 divided by 15. And that results into minus 27 divided by 15. The end result is minus 1.8. So these numbers are really important because this is just to calculate the Z-score. Later on, we're going to deal how to work with these numbers. And for that, we're going to use a table. There are 2 pages on tables 12.8 and also tables 12.8b, 12.8a and 12.8b. This requires us to read the tables, and basically what we have here is the following. The Z-score that is calculated, if you look at here, this is the 0 right here, and anything to the left will be negative. So here we have areas to the left of Z are negative values. So when we get negative values, what we're looking is at the value of the curve that is left to the Z-score. This is the value that we're calculating here. So if we have, for example, a value of, let's say, minus 1, right? Remember 1.0, and then you have a 0.00, 0.01, 0.02, 0.03, and so on. So you have to come to the Z-score that you calculated. Let's say, for example, you calculated minus 1. Then you have to go to the 0, if that's the one that you're looking for, and then the number will be here. You will select this value, right? This is the value that you will be selecting, right? So you intersect the 1.0 with the 0, if that's the one that you are intersecting, and it will be 0.1587. So that will be the way to read that table. Now, if the value is to the right of the 0, then we are going to use positive numbers here. And notice this one. The Z-score on the negative goes from minus 3.4 and it goes all the way to minus 0.0, which means that it covers all this area here. Okay? So you have a 0.0, which is in this direction, which is negative, and the last number here on the left will be minus 3.4. Whereas when the positive numbers you have here, now you're calculating the area of all this curve right here. Okay, the one that is shaded. So, but in this case, the number falls and is positive. And look, it starts with 0 and ends with 3.4. So it starts with 0 and continues to go all the way to 3.4. And if you look carefully at the bottom here, let's say that we pick up one value, 1.1, and we pick up again, let's say, for example, 0.00, then we'll select this number, 0.8643. If we were to select this number here, that would be like 1.1, right? And then with the 0, 0, which means you pick the first one, right? It will be this one here. And here will be 1.00. Okay, that's the way that you are going to be using those tables. And you pick this number. Now remember, if you continue to go, it will go on this side that is positive. It goes from 0 to 0.34. And look at the numbers. It's approximating 1, but it's not really 1. It's 0.9999, 0.9997, 0.9997, and so forth. So these numbers here are increasing to 3.4 for the Z-scores, but the table will approximate 1, 0.9997, 0.9997, 0.9997, and so forth. You can look at the table in the book. Become very familiar with it. It's going to be very important to know how to use this table. So here we have an example. And page 771, it says determine the area under the normal curve. So remember, when they're telling you about normal curve bell shape, you always draw the curve first, and then you start to calculate the values. So this says to the left of C equals to minus 1.00. B, to the left of Z, 1.19. To the right of C, 1.19. And D, between C is equal to minus 1.62 and Z equal to 2.57. So that's the example that we're going to practice. This is an interesting problem that you need to pay special attention. And here are the solutions. For the A, we have a minus 1 and it's to the left. So you need to use the table. And from the table, we are going to use the negative numbers. So C is equal to minus 1.0. Under 0, 0, we read the point 0.1587. Therefore, the area here is equal to this value. Okay. The B is the area that is to the left of 1.19, would be all this shaded area here, and that is equal to 1.1 under 0.09, right? So it's like you add 0.9 to 1.9, so you get 0.9, and we read 0.8830. Therefore, the area here it will be equal to 0.8830. This is just in fractions. If you were to multiply it times 100, it would be a percentage. And C, no, the total area of the curve for this one here is asking us for the shaded area to the right of 1.19. So basically, we have the whole area that we can consider to be equal to 1, right? 100%. In this case, we have decimals, so it would be 1. Therefore, it will be 1 minus the area that we calculated before, 0.8830, and this will result in, this area will be equal to, in decimal form, 0.1170. And now we have the case in which they're asking us to calculate what's in between these numbers, right? Between these numbers right here. Minus 1.62 to 2.57. So we need to calculate this area here. When they refer to the area under the curve, always they're looking at, this is the shape of the curve for the bell shape, right? So the area is whatever is in between this this point here that in the shaded area here. So how we do this? From the table, we look at the Z equals to 2.57, right? And then we read under the 2.5, and then the 7, and then we read 0.9947. Now for the Z equal to 162, we read 0.0526. So the area here is going to be basically subtracting the area that is given by this number. The area that is given for a number is everything here. And the area that we are given for 0.526 is the area that is basically this part here. So we're subtracting whatever we have all the way from here minus all this area here minus this chunk that is drawing in green. I don't know whether you can see the green, but it's right here, right? This will be here, this area here. And so the answer is going to be 0.9949 minus 0.526, and that results into 0.9423. So this is the technique that you need to use to calculate these percentages and the area under the curve. And we have another example. This example is not in the book, but it's a very useful example. They are giving us a standard deviation of 30, and also they're giving us a mean. The mean is equal to 180. This is given, and they want to know the scores, right? This represents the scores right here. And they want to know A, the scores that are above 258. And now, if you remember, we have our first standard deviation will be 180 plus 30, you get 210. For the second standard deviation will be 210 plus 30 will be 240, and the third will be 240 plus 30 will give you 270. And if you do on the left will be 180 minus 30 will be 150, 150 minus 30 will be 120, 120 minus 30 will be 90. This will be the where you tabulate and draw the standard deviations. One standard deviation to the right and one standard deviation to the left, two standard deviations to the right, two standard deviations to the left, and so forth until you get to the third standard deviation. This is the way you calculate these points right here when you're given this kind of data. And so now the question A, they're asking us the test score that are above 258. So basically they're asking us what's on this side of the curve right here. And for B, they say to calculate the test scores that are between 120 and 258. So basically, in that case, they're asking us what's underneath this curve right here. And now look, 120 falls within the second standard deviation. But this point does not. Therefore, we need to use the Z-score. That's when the Z-score becomes appropriate for this problem. So the solution. The Z-score for 258 is equal to 258 minus the mean, which is 180, divided by the standard deviation of 30. This results into 78 divided by 30 is equal to 2.6. Number is positive. So you will use the 12-point B curve to table to find the value here. Okay, so from table 12.AB, we get as the C equal to 2.6 points to 0.9953. Now that is basically the value or the area for the whole part here, right? It's all this one. So we need to subtract what that is, and we can assume that that's 100% or 1, right? 1 represents 100% unit. So it's 1 minus 0.9953. It results into 0.0047, and this is given in decimal form. If you multiply it times 100, you get 0.47%. 0.47% will be the answer for part 1. So that means that the number of scores, right, that are above 258 is equal to 0.47%. Now for part B, we need to calculate the Z-score of 120. It's equal to 120 minus 180 divided by 30. Remember, this is the mean, this is the standard deviation. This results into minus 60 divided by 30, and that's equal to minus 2. Therefore, we're going to use the table 12.88, right? 88. And the C for that value, it points to 0.0228. So now we need to find the score between 120 and 250, and that's equal to, remember, for the whole thing here, it is equal to for 258 was 0.9958. So we go 0.9958 minus the new value, and the value that we're calculating here is what falls on this part here, and that's equal to 0.0228, and the end result will be 0.9725, and this is in decimal form. To calculate it in percentages, you multiply times 100, so that will be 97.25%. And so if you look at the curve, it means that most of the data is basically falling under this curve right here, right? So that will be 95% of the one that you will get here. 97 right here. This will be like 97.25% is what you will get under this curve right here, right? And for the point that we get here is 0.47. This is very small percentage right here, right? So it will be about 0.47%. And basically, this is what we need to do in this kinds of problems. Again, if we were to summarize, right, we need to know how to use the tables once we calculate the C values, right? Once we calculate the C value, we need to know where is that the data is giving us, right? What's under the curve here? This is when the numbers are negative. This is when the number is positive. The other thing that we need to know is how to calculate the Z-score, right? The Z-score is a point that you pick on the x-axis. That would be your value minus the mean divided by the standard deviation. And you will, once you get your Z-score, then you use the table to locate where the position is that you are calculating. And basically, this concludes the class. Make sure that you do your homework, and I wish you the best for the next semester. Thank you very much.